hand it over to Sergi.
Thank you. Wow, so many faces. So happy to see so many people in here. As in previous seminars that we've held, I'll briefly introduce Marc first and then hand it to him. So Marc is a telecommunications engineer at the Communications and Architecture Research section at NASA JPL. He started in Barcelona, where he graduated in telecommunications and industrial engineering by the Polytechnic University of Catalonia. And he then moved to Boston, where in 2017 he received his PhD in aerospace systems by MIT. Now he's in JPL, where he's involved in a wide variety of projects spanning all layers of the protocol stack, from physical layer to network layer and above. He's the lead researcher in modeling and characterizing the multiple channels experienced between spacecraft landed in the lunar South Pole and the Earth, which is a topic of interest for NASA given the pool of missions that expect to launch in that area of the moon in the near future. He's also the lead systems engineer for a new deep space network demand access service for deep space operations, and regularly contributes to other tasks related to the DSN, the Mars Relay Network, and individual JPL or NASA missions. And along the way, he received many distinctions and awards, including the 2020 NASA Early Career Public Achievement Medal for his contributions to the Viper mission and the Human Landing System, or the 2022 JPL Explorer Award for his systems engineering leadership in the area of space communication. So we're very happy to have you here, Marc, and the floor is yours.
Thanks. That was too formal. So let's not do that. I'm just going to talk. If you have questions, you can interrupt and tell me, like ask a question or comment or whatever you want. I know we have someone that worked at JPL specifically on the DSN, so if you want to chime in, please feel free to do so. Okay, so what I want to do today is, this is not a technical talk. It's a talk about how we do things at JPL, how we do deep space communication. So I'll talk a little bit about different aspects and how things work. I'll give some intuition about what's going on behind the scenes from a technical standpoint, and we can then have a discussion or whatever. Okay, so keep this slide. Oh, a question about timing. So we're starting 15 minutes late. Is that okay? Okay. Okay. So I guess quick slide about JPL in case you're not familiar with it. We are a NASA center and not a NASA center at the same time, which has advantages and drawbacks. Technically, we are a federally funded research lab. That means that we belong to Caltech. So I am technically a Caltech employee and research staff at Caltech, but everything that has to do with our business space, or most of what we do at JPL, comes from NASA. There's a small part of JPL that works on classified projects for the Department of Defense, and then we have other projects related to, for example, the state of California. So like we monitor water reservoirs for the state of California because it's a big topic. We have 6,000 employees. That's our campus. It's in Pasadena, in the LA area. And what I like to say is, what you see is not real. It almost never happens, right? Like it's never this green and there's never snow there. It's a desert. Except, and I have never seen this except for this last year. You probably know that it rained a lot in LA for a week. It did look like this. So that's when we take these nice pictures. This is a nice slide that JPL put together to try and summarize the missions that we work on in general. So we are historically, we have been sort of the lead center for anything that has to do with deep space exploration. And the barrier between deep space and near Earth is somewhat made up, but we have agreed internationally that it's 2 million kilometers. So the moon is near Earth. Anything beyond pretty much anything after the moon becomes deep space. We are famous for, or most famous for, our work in the outer planets. So probes going to Jupiter and Saturn, the Voyager spacecraft, you might know, the two spacecraft that are outside of the solar system today. And then we're also fairly well known for everything that has to do with Mars. So JPL pretty much has exclusive access to Mars. We have done, I think, all the rovers and all the landers, that the US ones at least, that have landed on Mars. We have Ingenuity, which is our helicopter. We're working on Mars sample return, which is a campaign of several missions to return samples from Mars, from the Martian surface. And so what you see there, is this guy. So this thing, what's showing is a little rocket that will shoot from the Mars surface with rocks in it, and then that will rendezvous with another spacecraft that is being built by ESA, actually, because it's a partnership with the European Space Agency. And then that spacecraft will get back to Earth. We're working on Venus. Venus is it's a planet that is, there's a lot of interest in Venus right now. So NASA awarded 2 missions to go to Venus. The Europeans have their own 2. And maybe what's not so well known is that JPL has a lot of stuff in the near Earth domain. Not so much missions per se, but we do have a lot of payloads and instruments that we fly, and some missions too. So that's, you know, like we do different types of science. We monitor ocean height, we monitor CO2 concentration, amongst other things. So Sergi has alluded to the fact that I work in a section called Communication Research and Architectures. By the name of it, you can probably imply that it's more of a research section at JPL rather than implementation section. So we don't, our section, the main goal of our section is not so much to build flight hardware. There's another section at JPL that deals with that. We basically provide expertise on communication systems on an end-to-end manner. So from the BSN all the way to the spacecraft. We do that in the RF domain. We also do that in the optical domain. We do communication. We also do networking for missions. And historically, this section has been very famous for coding theory and information theory. So several well-known people in those fields worked at JPL in this section. And we were the ones, or they were the ones, because I wasn't there at the time, who developed coding for deep space missions, which was one of the first uses for having coded systems.
Perhaps most famously, the Turvey and Reed and Solomon.
Yes, right, exactly right. And others that have come after that, like Darius Solar, which, if you do information theory, is very well known. Other things we do, we do radio science and planetary radar. So we use, these are the antennas that we have as part of the Deep Space Network that we have available to us. These antennas do comms, but they also do other things like science. So, for example, one of the a recent article that was actually fairly publicized is we used this mission Juno together with one of our antennas to figure out how deep these Jupiter, what's called the Great Red Spot is, or at least bound the depth of that star to get a sense for how big it is. We operate something called the Goldstone Solar System radar, and I'll talk about that later, where we do planetary radar observations. We shine a planetary body, and we can figure out things like its orbit, its morphological structure, its surface roughness, and so on. And then a new part of the section, and I'm not really involved in that, so I'm not going to talk much about it. There's a big push in the section now that is related to quantum. And there's people who are working on quantum communications. There's other people who are looking at quantum more from a pure physics standpoint, doing quantum experiments. And so we have right now a payload on the International Space Station that is called the Cold Atom Lab, where we do experiments. And we do optical comms, right? Okay, so let's see. So I'll talk, there's many ways in which we do deep space comms. So I'll talk about some of them that I found were interesting. I will not talk about deep space optical comms, which we're actively working on, and we actually have a mission that is going to demonstrate that. And the reason that I don't talk about it is because I don't have enough time, not because it's not interesting. I'll also not talk a lot about the whole problem of navigation and timing, which is a big deal in deep space. On Earth, we kind of take it for granted because we have GPS. But when you go to Mars or you go to the moon, it's not an obvious problem how to know where you are and how to know what time it is. So there's a lot of work actually right now, especially at the moon, to figure out how we're gonna, if we're gonna have 10, 20, 100 spacecraft orbiting the moon or on the surface of moon. How do we know where they are? How do we keep time? How do they keep time, the spacecraft themselves, and so on?
Do you have slides on DSOC or for that matter, the lunar stuff that you'll be able
To share?
Yeah.
Not in this package right now. I can add some if you're interested.
probably be of interest to someone here?
Okay. What I will talk about is the Deep Space Network, what it is, how does it operate. I'll talk about how we use it to support critical events, and specifically I'll talk about Mars entry, descent, and landing, and solar conjunctions. I will describe a little bit the Mars Relay Network and how it works, and then depending on how we're doing on time, I'll talk about planetary radar and how we're operating, and I'll give you an example of some of the work that I've done. And I'll also talk about comm systems for ARTEMIS and the moon ecosystem. Okay, so the Deep Space Network is essentially, the easy way to describe it is a collection of large antennas that are grouped in 3 complexes around the world, one in Canberra, one in Colston, and one in Madrid. As you can see in the map, you basically, the general notion is you put them far apart in longitude so that you are providing coverage over the entire sky. At each complex, you have a mix of 70-meter antennas, which is what you see here below. So one per complex, as well as several 34-meter antennas. This 70-meter was built in the 70s, I believe, and we just refurbish it. We don't build new ones. All the new antennas that we're building are 34-meter antennas, and that just comes down to the fact that they're much cheaper. They're much cheaper to build, and we can now array those antennas to create essentially the equivalent to a 7-meter antenna. So, which when these were built, that wasn't possible. All of this is managed by something called the Interplanetary Network Directorate, and they are responsible for essentially managing the DSN, making sure that it stays operational. They also provide something called AMOS, which is the ground data system. So that's the piece of software that missions use in their operation centers to connect to the DSN and send data to the DSN back and forth. And so between the 2 things, you kind of get an end-to-end capability where that allows you to communicate with your spacecraft if you are a project or a mission. What can the DSN do? So there's a lot of information here. This is from our service catalog. It gives you a sense of, for each of the complexes, which antennas are there, and general capability performances like transmit data, transmit powers, and so on, and the bands that are supported. But generally speaking, the DSN can do, let's see, 1, 2, 3, 4, like 5 or 6 things. You can command the spacecraft, so you can send commands that you are generated, that the MOC, the Mission Operations Center, puts together to the spacecraft. You can get data from the spacecraft in different forms. You can get packets, you can get files. And when I say files, what I really mean is we provide something that is similar to FTP, if you've ever used that, where you can request a file from a spacecraft and so on. We provide something called beacon tone, which the easy way to think about this is like a paging system. And when I say paging, I mean like all the pagers where you have like a physical device that will just send you a small message being like, I'm alive or I'm not alive. That's the notion of a beacon tone. It's a very basic signal format that gives you that kind of information, but it doesn't give you everything, like the whole message. And then now we're deploying something called OMSPA. This is the moral equivalent of turning the DSN into an SDR. So the idea is the one thing that we can do is we can just take the INQ samples and ship them to you. And if you know what you're doing, then you can modulate the data yourself. Like we don't have to do it for you. And so this is something that we're deploying for CubeSats, for example, that don't have a lot of money. And so these antennas are expensive. So one of the ways that we envision supporting spacecraft is that are don't have a lot of money, or let's say that you have 4 different spacecraft. Maybe we just do a full spectrum recording, we ship it to you, and then you decide how to use that data. The network also does radiometric services, so that's mostly ranging to figure out how far the spacecraft is. Doppler measurements, which give you information about the radial velocity, so the velocity between the rate of change in the line of sight between the spacecraft and the ground station. And then we do something called delta door. Delta door is a measurement that allows us to get information about the velocity of a spacecraft in what we call the plane of sky dimension. So if Doppler tells you information about the velocity in the line of sight in this direction, delta door will tell you in that direction. And by having the two of them, you get a better sense of the full velocity vector, and that allows you to pinpoint the position of the spacecraft more precisely. The caveat with delta door is it's very expensive to do. You need 2 DSN antennas that they need to operate in tandem. It takes a lot of time because you're not just looking at a spacecraft, you're looking at a quasar too, and you use that as a reference. So it's a lot of time, and it's very expensive. So missions use it sparsely, they don't use it all the time because of that. And then there's other maybe less known things that the DSN does. So one of the things that we do with our antennas is we do atmospheric measurements to calibrate things like the troposphere at different frequency bands, and then we feed that information back into the radiometric services so that we can account for atmospheric services. Another thing that we do, and I'm not an expert on this, but I know we do it, is we take measurements to understand how the axis of rotation of planets move. So if you think about Earth, we kind of take for granted that there's an axis, like 3 axes that define latitude, longitude, and so on. It's the same for the Moon and for Mars and all of those planets. Well, somebody needs to measure that stuff. We do. I mean, I don't, but people at JPL do with these antennas. And then if you want to get time on our antennas and use them, there's a bunch of engineering services that come with that. So like there's compatibility testing that you do before launch to make sure that things work. And it's actually very helpful for missions because a lot of times they figure out that their telecom system doesn't work the way that they say it works. So it's a cross-check exercise for them, as well as frequency management and support of critical events. So I'll talk about that in a second. And the last thing I want to say is, in the previous slide, and when I talk about the DSN, I always show the antennas because they're large, they're big, they're flashy. Actually, there's a lot more to it in terms of the back end that makes the system work. So there's a whole lot of stuff that has to do with how do you schedule these antennas and how you make sure that you don't have conflicts and that you know what's happening, which receivers are busy, and so on. And then there's a whole world of frequency timing and distribution. How do you keep accurate time? How do you have exquisitely precise frequency references in the DSN? And that is an obscure world that I'm not too familiar with, but we need to do it, and we mostly need to do it for radio science. The driver is not so much comms. Comms doesn't need amazingly good timekeeping or amazingly good frequencies. But if you want to do radio science and you want to do things like bound, like understand properties of the atmosphere by measuring Doppler, for example, having an extremely good frequency source is very important. So those are the services. Now, these services can in order to actually make those services happen in real life, you can operate the DSN in different ways. So one way is, the normal way of operations, which is the simple one, is you have an antenna, you have a spacecraft, you point at each other. And what I mean by that, you point at where the spacecraft will be, right? Because if you're deep into the solar system, you have to take into account the propagation delay. So you point at where the spacecraft will be, and then you just communicate. That's the simple way. Then we have something called MSPA. MSPA is the ability to get data and transmit data to multiple spacecraft at once if they're in beam of the same antenna. And That's done routinely today for downlink. So we have more than one, usually 2 antennas that are constantly pointed at Mars 24/7. And those antennas usually are constantly doing MSP activities where multiple spacecraft, either on the surface of Mars or orbiting Mars, and sometimes their spacecraft are JPL and NASA, sometimes they're ESAs. They communicate all of them at once, and essentially what we're doing is a simple version of FDMA for that. Now we're working on being able to do multiple uplinks per antenna. That's a harder problem, and instead of doing FDMA, we're doing TDMA. Part of that is because there's only one transmitter, one high-powered transmitter per antenna, so we can't have multiple. We can have multiple transmitters per mission. The other problem, and when you have that, there's a slew of problems with Doppler recompensation and so on. So that's something that we're still working on. The same goes for antenna rating. I mentioned that before. That's the notion of you can take multiple antennas and make them work to synthesize a larger aperture. Notionally, 4 34-meter antennas give you the same performance as a 170-meter antenna. That's why you want to have at least 4 34-meter antennas per complex, because if the 70-meter antenna fail, you have redundant capability. We do that again. This is in the downlink direction. It's operational. We've done it for a long time. It's essentially beamforming, so it's not that difficult. In the uplink direction, we have demonstrated it with these antennas that you see here. That's the Apollo side. We have not done it operational. It's much harder to phase up the fields correctly in the far field when you're trying to do that planetary distances, and you don't have easy calibration targets that are nearby. So that's it's an area of work at the moment. And then the last thing that we've done is something called we call it polarization arraying. So that's the notion that if a spacecraft is very far away, one way to increase the data rate is to transmit 2 polarizations at the same time, and then on the ground we can receive both of them, and then we can and that hinges on the ability of the spacecraft of turning on two transmit high power amplifiers, which depends on their power budget and depends on their operational state. Sometimes it's not uncommon for our missions to have one of the 2 tweeters that is broken essentially, and so they would be able to do this. Okay, let's continue. So DSN. So how do you, let's say that you want to use one of those antennas, right? How do you even go about doing that? So the first thing is you don't just show up, right? These antennas are incredibly busy. We routinely have more demand for tracking time than we can service. There's just not enough of them. And we are building more, but the reality is we can't keep up. Like they're expensive antennas, and we only have so much funding and time. And CubeSats, small sats, they're exploding, and it's not gonna happen. So what we have right now is a process by which you can get time on our DSN antennas, and it starts during the mission development phase. You basically sign something that resembles a service level agreement with the DSN saying, I want to use these antennas for my communications. And then once you start operations of your spacecraft, what happens is today you are starting to plan the day of operations that will occur 6 months in the future. And it takes this amount of time because there's a first phase where all the missions that want to use the DSN basically put in requests, and we have a centralized management system for this. Then that system has a bunch of scheduling algorithms that deconflicts the schedule as best as possible. And eventually, what happens usually is that there's conflicts. It's just an impossible problem to solve for the optimizer. And so then there's a period of time where a bunch of DSN schedulers, together with the missions, semi-manually negotiate. I give time today, and I'll get it tomorrow, et cetera, until everybody's happy, and we come up with what we call the 7-day plan at the DSN, which is what you're seeing here for, I think it's one of the complex, I think it's meant. So for each of the antennas, each of the little box tells you something about what the antenna is doing at that point in time. So like week 19 of this year, the SS-17 was down, essentially, it was doing maintenance. You can see the SS-53, so SPP is Solar Parker Probe, that's one of our spacecraft that will support. Then we switch and we go to MRO and so on and so forth. You can also see that the SS-63, and at certain points in time, so like here or here, you're supporting 3 missions at the same time. That's an MSP activity, right? So you're gonna have these 3 spacecraft. This is Mars Odyssey, MRO, and Maven. These are 3 spacecraft that are orbiting Mars. They're all gonna be in beam of the antenna at the same time. So we're gonna make them work all at once using frequency division multiplexing.
I have a question.
Yeah.
How do you like filter out, or how do you choose between like who gets to use the DSN or not? Like, are there certain variables they look for?
So to the extent possible, we try to not have priorities between missions because it is how do you if you're choosing between a very large mission, right, and a CubeSat, then yes, I mean, you kind of know who's going to get bumped. It's not going to be the large mission. But if you're choosing between 2 missions, 2 large missions, like say MRO and Maven, how do you even choose, right? Like, so that's where it ends up being a negotiation where MRO will have a mission representative, Maven will have a mission representative, the DSN will have a scheduler, which is just a moderator essentially. And in the old days, they would sit in a room like this one and they would argue it out until they decide something. In the new way of doing things, you do it virtually via the internet, but you know, like it's the same principle.
But like, are there hard variables that you look for to make that comparison? Like for example, like the DSN, they're very high gain antennas. Do you look for the mission that absolutely needs the highest SNR possible, or like are there certain variables that can give someone preference over the other?
Usually not so much that. Things like how much time you have had in the past, you know, like it's more, it's not a, so this problem, it's not so much a statement of SNR, it's a statement of antenna time. How much time you've got in the past, how much are you trying to use in the future, and whether the amount of antenna time that you're requesting is commensurate with the importance of the mission. Yeah.
Yes, thank you. Just to follow up, obviously everyone would love to talk to their satellites as frequently and as much as possible, right? But realistically, with the current state of the mission, is it correct to assume that communication is one of the bottlenecks here right now with so many missions flying? Or is it not really the case? I mean, all this can be still very, very good, and you still have a gap between like the total capacity of your network versus what the needs are.
So I guess there's 2 answers to that question. From the mission perspective, whether you're constrained or not depends a lot on your concept of operations. Most missions feel, and there's it's a strange, interesting problem, right? Because most missions will tell you, oh, I don't have enough, impossible, like I need more. But then at the end of the day, if you tell them, you know, like, no, you're not getting more, they'll be like, oh, okay, fine, like I'll make it work with what I have. So that's a statement of the mission side of it. Then there's a statement about how busy are the antennas. So I think our schedule, so if you take the total antenna time that we have available in a year, let's say, and you look at how much time where the pool of antennas actually doing mission support, it's about 70 to 75%. And it's kind of hard to go beyond that if you think about it, because you have downtimes, you have spacecraft emergencies, which basically so there's a process by which a spacecraft can declare an emergency, and when that happens, it's the only case that you can get bumped, right? Like if you're in that schedule, that track is happening to you unless somebody declares an emergency. Yeah, exactly. And then that mission gets priority and everyone gets out of the way, but it's still a negotiated thing, right? Like the DSN doesn't make the decision other mission needs to give priority to this other mission because they have an emergency. The DSN will call that mission and be like, listen, there's this other mission that is, and if they say no, it's a no. But missions don't do that because all missions experience emergencies and we all play nice because otherwise it doesn't work. Right here. Okay. Okay, so let me give you a sense for what are the data rates that we can do from the solar system. So this is a plot that tells you distance on the x-axis, astronomical units. And on top, so here in this part here, I give you a little intuition of the distance between Earth and the moon, the planets, and I put the Voyagers because they're the furthest thing that we communicate with. So that kind of gives you a sense of what is the absolute upper bound. This vertical line is the fictional definition of deep space and near Earth. So technically speaking, it's 2 million kilometers, which is here, roughly speaking. And the point of the slide is to show that with our antennas, despite the fact that they're large, we are definitely in the power constraint regime, right? Like there's a 1/r² slope over here. And if you are at Voyager distances, you're talking about 100 bits per second. And that's what we do operational, right? Like when we talk to our Voyager spacecraft, we have tracks that last for 6 hours. And for 6 hours, information will trickle in at 100 bits per second. Now we're looking at ways to improve these. We can probably improve these by maybe 10 dBs, an order of magnitude further. Beyond that, it starts to get really, really tricky. You really need to get a lot of antennas and array them properly in order to get much further than that. The other thing that is not obvious in this plot, but I think is that you probably should be, if you study communication systems, you'll probably realize is that you don't do a mission will start, let's say that you have a mission that is going to Saturn. That mission will start at a planetary distance or at a distance from Earth of here, essentially, right, before the moon, and it will go all the way up here. So the radio that you put on the mission and the DSN needs to support a fairly extensive range of modulation and coding options, so that as you get further and further, you can actually do these, right? Like in order to trace this curve, what is happening in the back in operations is you're constantly, and when I say constantly, maybe on a monthly basis, changing your modem and encoding to always operate at an optimal point. Which we call it variable coding and modulation as opposed to adaptive coding and modulation. Adaptive coding and modulation is what you do on Earth, where you can negotiate which coding and modulation you're using to optimize the link, like DBBS2 does that and so on. We don't do that. We do it sort of manually by planning, partially because the timescales in which we have to do it are larger, and partially because the propagation delay means that anything that has any form of communication that implies round trip line time, once you go past even Mars, it's just none of it works, right? Like you have to plan, everything is planned ahead in advance. Okay, so let me talk about entry, descent, and landing and how we do that. So,
Can I ask a question?
oh yeah, sorry, go ahead.
I was just curious about the frequency that you use to communicate. Yeah, and how much bandwidth,
So most of the deep space missions use X-band.
Okay.
The amount of bandwidth available is set by, ultimately is set by agreements that are done at something called SFCG, Spectrum Coordination something group.
Okay.
And what it is essentially a bunch of representatives from space agencies coming together and agreeing. And we do it at the agency level for civilian space. So the DoD will do other things, and then like Starlink, it's a different process for them. It doesn't go like something.
Roughly like what range is next band? Like
Oh.
measures very low frequency.
For you guys, it is, yes. So uplink is 7.2 gigahertz.
7.2
Gigahertz.
gigahertz.
That's for uplink. For downlink, it's 8.4 gigahertz. Ka band is 32 gigahertz for downlink and 34 gigahertz for uplink.
Downlink for the near Earth missions with Ka will also use 26 gigahertz.
That's right. I call that K band, but yes, that's right. And then we have a handful of missions at S band. That's 2.2 gigahertz. Okay, so entry, descent, and landing. Hopefully you've seen this before. This is how we go from, that's how a spacecraft goes from an interplanetary trajectory between Earth and Mars all the way to the surface. So you have the vehicle coming in, it enters the atmosphere. Here you have like the peak of heating where you have the heat shield completely burning. Then at some point you deploy a parachute, you jettison the heat shield, and then when you're close enough and you have a radar working here to determine how high you are, and then at some point there's a little crane, we call it crane, that plops off of the white shell. It has thrusters to stabilize itself, and that thing takes the vehicle up to, I don't remember, maybe 10 meters up the sky or something. And once you get to that, the sky crane stabilizes, and the vehicle itself is lowered from that. And it's literally like a crane where you have a cord that lowers the thing. And then the sky crane goes away so that it doesn't crash on the vehicle. That's this part. So the question is, how do you know? So this is happening at Mars, right? Like we're Mars, the round trip lifetime delay at Mars is 4 to 20 minutes, depending on how the planets are aligned. So this whole sequence lasts 7 minutes, and you never land on Mars when the planets are closest. So that means that this needs to happen all on its own. And when we hear from it, it has already happened. Like you don't joystick any of these. Like you just, all you're doing is you're a spectator after the fact. So how do you communicate during these in such a way that we know that this thing has worked? Because it's a fairly complicated sequence of steps, and it's difficult for three reasons really. First, when you're up here and you have the heat shield burning, you don't have comms. This is called the plasma blackout, and it happens every time you enter a planet, including Earth. Okay, so that's that. But then, even when you're in this phase here, you have two problems. One is there's enormous deceleration that happens, for example, when you open the parachute or when these thrusts fire. You don't know when that's going to happen. So it will happen. All these things happen whenever the spacecraft senses that it's at a certain altitude above the surface, then it happens. But you don't actually, we can't predict that well enough to be like, okay, the spacecraft will decelerate at this point in time, and that's when we'll experience an enormous Doppler. And then on top of that, this thing is on a parachute, it's swinging back and forth, so you can't point high gain antennas. So you're stuck in a position where you have extremely low power because you're trying to communicate with Mars from a low gain antenna, like a patch antenna essentially. And you have enormous Doppler shifts. So this is a plot of the predicted Doppler shift. And as you can see here, there's 3 plots because it depends on how you enter the atmosphere, which we can't really predict all that well. The span of these is 80 kilohertz. And that happens over a span of 7 minutes. And this plot here is the derivative of this plot. So this is the change in Doppler rate and these huge spikes. I think it's when the thrusters fire. So you look at that, And essentially what that tells you is that any form of normal communication that we can think of, it just doesn't work, right? Like, for example, you cannot even track a carrier. Any form of system like a PLL, or you can't, it doesn't work. So all that we do in this scenario is we use tones, which is essentially a way in which you transmit a subcarrier, and the frequency of the subcarrier tells you something about where you are in this sequence. And then to receive this tone, we use our DSN antennas, and we use a special receiver that uses FFTs. And all you're doing is you're doing FFTs. You don't have any phase information, and you in real time are doing some Doppler compensation, which I'm not going to go into details, but the notion of it is, if you think about an FFT plot, you want your carrier to be at 0, and then all you're doing is you're measuring the separation between the carrier and the tone, and that separation tells you where you are in that sequence and whether something has succeeded or not. And on top of that, we don't do it with one antenna, we do it with multiple antennas in multiple complexes, because if one complex fails, then we can have another complex. And we do, so our largest antennas is 70 meters, I mentioned that. There are larger antennas in the world, like the Green Bank telescope, that's 100 meters. So usually we bring our own receivers to that antenna, we connect them, and we get time on that antenna. And so we have a network of antennas, and the Indians do it too. They also have a 100-meter antenna, kind of listening on all of these activities all at once to make sure that we understand if things worked or not. The same principle is used for communicating a low solar angle. So this is my not very good diagram about when you get in trouble, right? So if this is Earth and you have a spacecraft that is here, the sun is in between. Well, if the sun is in between, you're just not communicating, because you're not going through the sun. So that's really simple. If you have a spacecraft that is either here on this red dot or here in this red dot, we call that solar opposition. And depending on whether it's here or here, you can communicate on one direction or another, right? Like if you're here, you can do an uplink, so you can transmit from Earth to the spacecraft, but you can't do a downlink because the sun is behind Earth. And if you're here, you can do a downlink, but you cannot do an uplink. Now, the other thing that we do is when you're close to the sun, you can actually also communicate. And we have, by measurement, we have models that tell you how is the sun. So the sun does two things. It adds noise out of it, which reduces your SNR. It also causes what are called scintillation effects, which are essentially, it's like fading. That's what it is. Like cell phone fading, where you see dropouts in your receive power, and you see random phase shifts that happen because of the solar plasma. And what we have done, and that's what I'm showing here, is we've measured as a function of this SEP angle is the angle between the center of the sun and the bore side of your antenna. And so we've measured over the years this scintillation index, which tells you the strength of fading as a function of that angle. And so we have flight rules that tell us if you're operating at X band, you can only communicate up to that point in a certain mode, and beyond that point, you have to switch to another mode. And then after that, well, you better put your spacecraft in hibernation because you're not talking to it.
You mind elaborating on what kind of modulations you tend to use? Are we talking about the standard modulation that people use on Earth, or you use very sophisticated signal processing there?
So that goes back to my plot about those curves.
Yes.
Power efficiency is the name of the game.
Yes.
So PPSK, large or small coding rates. So like one turbo codes rate 1.6, LDPC rate 1.5 are typical. At least LDPC is used in one mission. Newer missions are starting to adopt LDPC now. We use something called concatenated code, which was a convolutional code plus a Reed-Solomon code, rate 1.5 also, roughly speaking. No pulse shaping, because pulse shaping gives you it's a power hit, so you don't want that. And then if you don't have enough power, we transmit on subcarriers. so that you can have a clean carrier for carrier synchronization.
Do you do any repetitions or like direct like the physical layer or?
We do repetitions, but we do them manually at this point.
Okay.
So
Okay.
yeah, if not all the data that we want has come through, someone will count the bits, roughly speaking, and we'll uplink the community.
Being do it select the back for you. Okay.
Sorry.
You have a human being do it basically select the proposal that you're trying.
And that's
Okay. Okay. Good.
and it's not a human being, right? Like we have tools on the ground that help us do it. Well, I mean, we're not. Well, I've heard stories from the 70s of people looking at beats one by one. So like it has happened. It doesn't happen, and we are starting to transition to a point where we're going to have like more automated repetition schemes to get away from that.
Thank you.
Okay, so
Round trip time is about 15 minutes. You know, you get that spare time.
You can't read that much copy, I understand this.
so they're not very sophisticated. No,
Thank you.
but even those break here. So when you get to like, for example, at X-band, when you get to like 3 dB, to 3 degrees from the sun, it all starts to break down. And then what we're gonna start doing now is, before what we were doing is we had a hard cutoff at 3 degrees. We said no more. So plan your operations so that when you get within 3 degrees of the sun, you get in hibernation, and when you come out, we'll talk to you again. Now we're starting to transition to a mode where we're gonna use the same concept of the tones, the frequency tones that we can modulate using FFT methods to communicate, to at least have 10 beats per second or so until you're really, really close to the sun, and then again, like you can do it.
Maybe just a quick follow-up here, or talking about the power, do you need power control, or is it effectively max power all the time it's fitted from ground to satellite?
Well, it's max power all the time, except when the mission is beginning, right? Because
Right.
if you're close enough to Earth,
Yeah,
you're
not the further radius.
yeah.
Okay.
But the dynamic ranges are enormous. So, but they're also predictable ahead of time. So when you do the whole scheduling business, you can configure all of that. So like there's a lot of work that has to do with configuring that correctly. But ultimately, if you are at Mars or beyond, it's pretty much max power.
What about the satellites? Do they have, realistically, most of them control of the TX power? Is it often used, or is it like they transmit at the max power and you just don't have this complexity there?
Yep. No, you just scream as loud as you can. In fact, again, because power efficiency is what you really care about, you really want them operating at saturation power.
Right, that's right.
And also, it's better for the tweeters in general, right? Like not change.
Yes, exactly. That's yet another thing that can break.
Yeah.
Thank you.
I remember at JPL, there was like a lab that that builds sun shields, like to protect spacecraft from the sun and like kind of deploys that distance. Like, when do you decide whether to actually put that on a mission and use it, like, versus not to solve this problem?
We don't use it for that purpose. The sun shields are used usually to shield instruments if we have them. So like, and usually sun shields are used for, so for example, solar particle probe doesn't have a sun shield that deploys per se, but if you look at a picture of the spacecraft, it's like an asymmetric spacecraft where you have a huge chunk of ceramic material, I don't know what it is, on one side and everything else on the other side. And that side is the one that is facing the sun all the time. Solar particle probe is doing helio science, so like it swings close to the sun every now and then. But for these, we don't, right? Like missions don't want complexity, and they don't want to take a sun shield. If you put a sun shield for something like this, it's mass that you need to carry that you could be using for another instrument that helps you on your primary mission. So they'll always take that, and then they'll modify their operations to just cope with these however they can. Okay, I don't know how am I doing on time.
Wildfire.
Okay, Mars relay ops. So how do we operate our stuff on Mars, and how do we communicate with the spacecraft? So this is an old product, and things change. We get better. We automate things. But roughly speaking, this is how it works. So what you have here are two timelines. This is Earth timeline. This is Mars timeline. Night at Mars, day at Mars, night at Mars again. So the rover wakes up and receives a bunch of commands from the DSN direct to the rover through an X-band uplink. Then it spends 6 hours or sometimes less, depending on the state of the rover, actually doing operations, moving around, doing science, whatever it is. After that time, the rover stops. The rover doesn't communicate and move at the same time. It always is completely stopped to communicate and transmits a bunch of information via UHF to a relay orbiter that is overflying the rover at that point in time. And the time at which this happens is carefully managed by something called MEROS, which is a system that is sort of similar to the DSN scheduling system that I can broadly speaking. The relay orbiter takes that data and puts it in its buffers, and then sends it at the next contact opportunity with the DSN on a normal downlink. We call these data quick loop data or decisional data, depending on who you talk to. This is data, and to give you a sense of the data volume, we're probably talking about 100 megabits or 100 megabytes or 200 megabits, something like that. So it's not a lot. But the notion of it is that this is the data that is critical to get early enough so that people on Earth can look at it and decide what the rover will do the next day. So, and then this cycle sort of repeats constantly. So whatever you get from these decisional pass, we call them decisional passes, it goes to the operators, you do some initial data science, you do activity planning, and this activity planning is for the next day. You do sequence generation, you do sequence validation, because you never uplink something to the spacecraft that you haven't validated with your engineering unit in the lab. And then the cycle repeats. Additionally, there's usually a second pass that happens in the afternoon or night, but that's what's shown here, which returns what we call bulk data. The bulk data is other science data that we don't use to actually plan the next day of operations. And that's also done via the relays always. And the data volume on this guy is maybe 500 megabits or something like that. So again, not a lot of data, maybe some more is depending on the spacecraft. And essentially this repeats indefinitely. The only time that things change is if you look at this is supposed to tell you the shift of the operators that here on Earth. And essentially, we don't want people working at night because people get tired and you have to pay them overtime. So we don't do that. So what happens in reality is we time things so that operators work from 6 a.m. to midnight, essentially, on a sliding window basis. So today I show up at 6, I work 8 hours, and then tomorrow I will come at 6:15 and I'll work 8 hours, and so on and so forth. And that time shifting happens because the Martian day is a little bit longer than a Earth. And every now and then, whenever this prime shift would have to be at night completely, we just stop operations. So we put the spacecraft, the rover goes to sleep, we just leave it sort of like in a dormant state, and until the prime shift starts back at 6 a.m. or whatever, we don't operate it. So that's the notion about how it works. The Mars Relay Network is essentially these 5 spacecraft that you have in the table at the bottom. And what they do, these are spacecraft that were initially sent to Mars for scientific purposes. And during the prime time of their missions, they did no relay communications at all. They just did science. Once they're done with their primary mission, they are reconverted into relay spacecraft by changing their orbits. And sometimes they're not just relay spacecraft like that. They become dual purpose spacecraft. What that means, for example, one of the consequences of that is that they're all spacecraft. So if you look at the dates, 2001, 2003, 2005, and then these are the two new ones, 2016 and 2013. They're also not all NASA. So there's 3 of them, Odyssey with MRO and Maven that are NASA. The other 2 are ESA spacecraft. Everything's interoperable. We use something called Proximity 1 protocol. Proximity because we call the link between the surface of Mars and the spacecraft a proximity link. By using this protocol, we make sure that we can have cross support where a Mars orbiter can provide support to one of our rovers. That Mars orbiter will talk to an ESA station, and then the ESA station will relay the information back to the mission operation centers at JPL. And we can do the same thing for the European Space Agency vehicles. In terms of capabilities, so the link between the surface asset and the orbiter is a UHF. We do have adaptive coding and modulation implemented on those radios, and we use that routinely. We also have a full-fledged go backend ARQ mechanism where the radio on board the relay can request for retransmissions if needed. What we don't have is multiple access, and that's starting to be a problem because we have more and more missions going to the surface of Mars, and sometimes 2 missions are in. So in a given overflight of a relay spacecraft, there's 2 missions that are in view of a single spacecraft. There's 2 landed assets that are in view of a single relay satellite. And then what we do now is we just say, okay, the first half of the pass is for this mission and the second half of the pass is for the others. So it's very manual in that sense. These relay spacecraft do more than just data transfer, just like the DSN. We do full spectrum recordings or open loop recordings of INQ samples at limited rates. And the biggest bottleneck here is not the proximity link or the relay spacecraft, is really how do you return the data from the relay spacecraft back to Earth on the deep space link. If you've ever worked with INQ samples, you know that the size of the files grows large very quickly. So the bottleneck is the other link, not this one. You can take radiometric observables from the vehicle to help you figure out where the surface assets are. So you can do ranging and Doppler. And you can do time correlation and time transfer, which is something that I mentioned before is a big deal. And I can't talk much about it, but you can. The way it works essentially is we have a notion of what is Earth time, and then we have a notion of what is spacecraft time. And there's a table that you periodically measure that tells you what is the offset between these 2 blocks. So one way to measure that offset for the vehicles that are landed on Mars is to use these relay spacecraft, as opposed to having to have the DSN antenna talk directly to whatever is on the ground.
Yeah, talking about some numbers, maybe some of the takeaways I'm going to see are if we talk about the relay that stays on the Mars orbit, potentially may need to store a bunch of data, as you mentioned, right, before bumping it back to Earth. What kind of sizes for the memory do we realistically talk about? Is it hundreds of megabytes, gigabits, terabytes? I don't know.
Let's say a couple of gigabytes right now. These are old spacecraft.
Yes.
So it's not a lot. And the memory on board the spacecraft is deterministically partitioned between what is used for relay activities and what is used for the science instruments of the actual spacecraft, right? And so in a way, the way that it works really is from the point of view of the spacecraft, the radio that is doing the relay is another instrument. That's how that mission thinks about it. It's not really a radio, they don't care. All they see is this is another instrument that I'm carrying and I have to transmit that data.
Right.
What we do though is we do prioritization of the data on board the spacecraft. So we'll send first the telemetry data from the relay. Then we'll send all the data, then we'll send, so if I go back, then we'll send any data that you have that is decisional data from the surface asset. And after that will go the bulk data from the spacecraft and so on.
Yeah, very, very reasonable.
Yeah.
What is the layer you store the data? Is it basically the bits or talking about the IP samples that you try to kind of get? So basically, whatever the physical layer told you, right? You don't do any repackaging, any.
So we're storing the moral equivalent of Ethernet frames.
Okay. Okay, got it. Any compression by any chance? Or is it inappropriate there? Okay.
Nothing. You receive the transfer. We call them transfer frames in our parlance, but it's essentially an Ethernet frame. You store those.
When will the next Mars landing happen, and what is the goal?
So the big thing on Mars right now is Mars sample return. So we have a rover right now, Mars 2020, has just collected a bunch of sample rocks. Some of these rocks have been dropped on the surface of Mars. Some other samples are actually stored inside of the rover. The next thing that we're gonna land is it's a lander that carries the Mars ascent vehicle, and the notional plan is the rover that has the samples in its belly is gonna rove all the way to that lander. It's gonna drop the sample that it has internally next to the lander, and then that lander has an arm that will pick up these samples from the ground, put them in a rocket, and then that rocket will shoot up to Mars and get to Mars orbit. And then a NASA spacecraft or a European spacecraft will swing by, catch the samples, and then go back to Earth.
Is it going to be the same type of design that was done in 2000 when, no, it's completely different?
Different, and that's partially because the next vehicle is not a rover, right? Like it doesn't have to move. It's a lander that needs to be able to shoot up a rocket. So
I'm familiar with that one. The fear is not there. It's, you know.
And then there's as a side note, there's going to be a bunch of helicopters. I think it's 2 helicopters with little wheels that are going to be there as backup if the arm fails, or the current rover that is supposed to take the samples to the lander that will shoot the rocket up. If that thing fails, we're going to have helicopters that are going to be able to go pick up the samples that have been dropped on the ground.
Backup.
Yeah. So.
Can I help ask, like for Mars Q1 and Q2 set, the Marco CubeSats, or do they just use a different protocol? Like is that why you don't have them on there?
They didn't use actually I don't know. Did they? I don't know. I'm not sure. So for the deep space link, they don't use Prox1, that's for sure. Right, like the
X-band, right?
that was an X-band link.
Right.
For the recording, so the whole purpose of Marco was to record the entry sequence, right? And I don't know off the top of my head if they did just a full spectrum IMG recording of that, or they actually were demodulating and recovering the transfer frames and then sending those to the IDS link. So I can't answer to you. No.
I want to say that Marco was specific to the InSight lander, and so I don't know if InSight is compatible with this.
It was, yeah.
Okay.
InSight was compatible with what we said. Sorry.
So like, I'm a little bit curious about this question. So like, in the context of interstellar exploration that we try to do, like by sending some like light sails, solar sails to the next habitable like planet, exoplanet. So we really tend to use like near infrared wavelengths and also more visible and more blue. So those are the best actually theoretical ones. So like, are those frequencies or like those ranges also useful for interplanetary exploration or like this kind of your mission?
I'm sorry, are you talking about optical or terahertz comms or which
infrared, like near infrared.
Infrared.
Yeah, because like you always talk about like gigahertz or L bands to expand.
Yeah, so this is why I said at the beginning, I can't talk about optical comms because I'm already running late and I can't talk about anything. So optical comms is a big deal, right? Like the one thing that the one thing that gives me pause, especially if you're talking about interstellar comms. So the most efficient way of communicating in optical communications that doesn't rely on quantum entanglement or, like, I don't know, like that stuff, I haven't looked into detail. Maybe there's something more efficient, but like more traditional optical comms, it's photon counting, which basically means you count how many photons are arriving. And so we demonstrated analytically that the best way to do that is something called PPM modulation. And the caveat with that is that if you look at the capacity curve for PPM, it has two regions. It has one region that decays at 1/r squared, and then at some point it transitions, and it has another region that decays at 1/r4. And so that is not great, right? Because that means that if you go too far, then your performance starts decaying at 1/r4, and if you go out of the solar system, you're definitely in that region. So you might end up with a performance that is worse actually than with RF. So I have my doubts, to be honest with you. I will also say that if you're very far away and you wanted to return a lot of data, the best way of doing that is to not transmit the data, is to just physically bring the spacecraft back. Because at some point, R2 and R4 overshadow anything. So just make it so that the spacecraft comes up. It doesn't come back to Earth. Like, you don't have to land the spacecraft to Earth, right? But you can make it come closer. So, yeah, thank you. Okay. What's that?
At most, we'll have used you for 5 more minutes.
Okay, good.
I know that people will probably, we could use you for the rest of the day, but it's not fair. So let's call it that.
Okay, so I'll skip that part. I'll talk about this because this is a big deal, and like it's NASA is spending a lot of money on this. So the moon is the next big target. We want to go there. It's not going to be like the 60s where we went there and then we left and didn't come back for like 50 years. The whole point is to go and to create a way to have sustained presence of humans there. And specifically, the place we want to go is the south pole of the moon. And the reason why it's showing that plot over there, we know that plot is showing you areas where there's concentration of water on the lunar south pole. Now, these are not lakes, obviously. It's not, and they're likely not even ice of sheet. It's more likely water that is embedded in rocks somehow, and so you kind of have to crush the rocks to actually get to it. But we know it's there. We don't know how much. We don't know exactly in which form. So a lot of interest of going there is, well, there's a couple of reasons, right? Like, one is if you have water, you can use that water for many purposes. One is to drink if you have humans. One is to breathe. One is to create fuel. And then in a long-term vision, you can use that fuel to go to Mars from the moon as opposed to going from Earth, which has its own advantages. The other advantage of going to the moon is that NASA thinks that the moon is a good playground to demonstrate technologies for Mars and for human Mars exploration. And that's sort of hinted in the thing on the right? Like, you see the moon here saying, oh, the moon is a near term, but Mars is a long-term goal. That's really, part of that. And communications is part of that technological effort. There's obviously a lot of other systems like eco systems for life support habitats and so on and so forth. So it's a big it's a big endeavor. Now, a couple of difficulties about going to the lunar south pole that are specifically related to comms. So the biggest one is this, which I spend a lot of my time working on this, which is if you are in the lunar south pole, it's kind of like being on the poles here on Earth, where the Earth never rises very high in the horizon, right? Like, it just kind of like lingers at low elevation, and it's just, well, I mean, so if you're in the lunar south pole, what happens is Earth is always there because we always see the same face of the moon, right? Like so from the point of view of Earth, you're always kind of seeing the moon in the same location, the Earth in the same location. And then the sun is going around 360 around you, kind of the way it does in the Earth poles. So that creates the possibility for a multipath channel. And that's a big deal. And it's a big deal because none of our systems are equipped for this, right? Like deep space comms was the ultimate AWGN channel, an enormous antenna pointing at the void. So all you had was noise, white Gaussian noise. So there's been a lot of effort to try and understand what these reflections look like, what are their characteristics, how powerful they are, and how they will affect this link. There's been a lot of effort also in trying to understand with the current technologies that we have implemented, for example, in the DSN and in our flight radios, what is the performance of this link and how much degradation we can expect on the link because of this multipath issue. So I'm doing a lot of work on that. In fact, I'm going next week. I'm going to an antenna to install an open loop receiver, so that we can. There's a mission that is going to the lunar south pole, hopefully in a couple of months, 3 months. So we are hoping that we can do some full spectrum recordings of this multipath phenomena and start, understanding this channel a little better. Okay, this is my last slide. This is the vision for what people want to do at the moon, and when it comes to communications, it's called LunarNet, and it's this idea of the moon, both surface users and relay users should be part of a broader ecosystem of near-Earth network. One way to do that is using a technology called DTN, delay tolerant networking, and that is not a I guess for reference, our radios stop at the Ethernet level, right? Like there's no notion of an IP address in our spacecraft. DTN is a way to kind of like introduce a network layer functionality to the whole system. So this is something that we're working on, and it's an interesting problem in and of itself, right? Like on Earth, links are always available because you have a cable all the time, or you are connected to an access point that has a cable somewhere. That's not how this is, right? Like this is lunar ecosystem, things go, there's the far side of the moon and so on. Okay, so that's it.
Time for one quick question, I guess, the audience.
What about interoperability and security of the communication? Because I've seen a lot of protocols, but especially with respect to the moon, we know that NASA may be not the only player in the environment. So how we can secure stuff?
Okay, so that's a good question, and I haven't mentioned anything about that. So up until recently, NASA did not have a requirement to encrypt anything. And so our spacecraft are not encrypted in any way. If you know what you're doing, you can command one of our spacecraft. You have to know the data formats and stuff, and you have to have a large enough antenna to talk to Mars. But everything is completely open. NASA has realized that this is a bad idea. And so in 2019, they had a requirement to encrypt all of our uplinks, not the downlinks. The downlink data is usually science data. We don't care if people see that. NASA is a public entity anyways. And there's different ways to do that. For now, encryption is only a requirement for near Earth. And remember, the moon is included in this. Anything past the moon, essentially, we don't have to do it. Although it's coming, right? Like at some point, NASA will say, no, you have to encrypt everything. So we at JPL are working on this because even though it doesn't affect most of our spacecraft, it will eventually. Now we have two ways of securing our spacecraft. One way that is basically applying security at the Ethernet level, so to speak, and that would work well for point-to-point links, which is, for example, like if you want to secure a link with an orbiter to Saturn, that works just fine. It's a point-to-point link between the DSN and the spacecraft. For a network-like ecosystem, the moon or Mars, what I showed before, that's where DTN comes in. And DTN is the protocol that NASA is banking on. And if you look at what it is basically a protocol that allows you to do store and forward capability because links in a space network disconnect because you're orbiting a planet. And then on top of that, there's an accompanying protocol. So there's two protocols. There's bundle protocol, which is essentially a packet, so to speak. And then there's something called BPSec, which is the moral equivalent of IPsec. And that's how we think we can secure, like communications in a broader ecosystem with commercial planes.
Well, thank you everyone for attending. We have here a reminder that we have here some posters that Marc brought for
Please take them.
And if there's leftover food behind,
There's nothing left.
No.